Okay, let's get started. Uh, Today's talk seminar is about bringing IoT, Internet of Things, into daily life. This is the joint work of Professor Mahant Gowda and from Penn State University and his student Taiting Lu. Both of them are supposed to present this talk together, but because of a family situation, Professor Gowda could not attend today. So Taiting will present the whole talk. He's pretty good. He'll do a great job. Taiting is a PhD student at Penn State University. He got his bachelor's in computer science and also in electrical engineering from University of California, Irvine. His area of interests are in anything related to sensing, sensing hardware, sensing algorithms, and he has published in pretty highly selective conferences like Mobicom and NSDI. Okay, and he got the best paper award at IoTDI, Internet of Things Design and Implementation Conference. It's pretty selective conference, and also he was selected for NSF iCorps program, and this program is tries to encourage researchers to productize their research, bring ideas into marketplace, and so a lot of research that Titan does, it has practical applications. Okay. With that, you can go ahead, Titan.
Okay,
Thank you.
thank you, Dr. Shari. And then please let me share a screen. Okay, thank you for introduction. So my name is Taiting, and this is a great honor to be here to present our works with you. And we would like to share some works that we have done in Dr. Scotter's lab and in the space of IoT. And so at the beginning, we want to give you some introduction of IoT. So the IoT means that Internet of the Things. So despite that the sensor embedded smart wearables has been envisioned for many applications in the areas of the fitness checking, like gesture analysis and healthcare and the sports analysis. So there are still many problems or difficulties we need to solve. So today I'm going to share some stories of our experience of in how to bring the smart wearables in the daily lives. And I will sample some papers and I give a quick introductions and go through this paper to discuss how do we implement or bring the IoT into our daily lives. So at the beginning, I will discuss about the sign language recognition and translation. So you can see there's a big need in the sign language. So we use the smart rings to detect the finger motions of the users. So we can use some analyze the finger motion to analyze the sign language, to recognize the sign language. And secondly, we can use the earphone to detect the motion of the air kernel to recognize the facial expressions of the users. So this is enables our daily life like healthcare for health monitoring. And also we will embed the smart sensors inside the board like credit to analyze to check the board's 3D trajectories and rackets of players. So these three words this is our main discussion topics. And for the first word, I will introduce the OmniRing. So this is the OmniRing platform is a joint work by with Professor Gowda and my colleagues during the Penn State. And this is the smart ring platform and designed to integrate by integrating the low-cost electronics components like smart sensors and using the flexible PCB to able to bend the PCB in the shape of the ring for 3D finger motion trackings. So, and we will discuss, and as you can see in this picture, this is the rendering picture. So we can see is that the ring has the two sensors, our IMU sensors and the PVD sensors. So why do we want to do this work because currently for wearables, there's many wearables currently in the markets like OmniRing, gloves, wristbands, but they have the limitations in capturing the 3D finger motions because of their form factor or because of their power consumption. And also they need to calibration because of the different location. We have a different compass or environment settings. And also there's no disclosed hardware design for developers or for researchers to further develop their sensors or platforms. And also there's another solution like using the cameras. But for the camera, those we have like well built and high quality data sets. But this data set has a sensitive to the environment lighting, like occultations or lightings. And also there's some privacy issues. And also we cannot bring the cameras, like it's not like portable, easy. So regarding this, we want to discuss some main challenge or some solutions that we can have. So firstly, some commercial products are closed source and no access to the road sensor data like OmniRing, which is the famous branding in developing the smart rings products. But they are not, because of the commercial reasons, they didn't disclose their designs. So we decided to bring or design our new platform. And then we plan to open source to everyone, to the researchers, to further develop and use our platform to do the further research. And also, there's no private work embedding all the electronics or components inside a single ring. Because of the difficulties of the design of PCB, so this is not easy to develop or design to embed all the sensors, microcontrollers, or antenna into a single PCB, and even bent in the single and as a form of ring. So that's why we designed a sensor embedded smart ring by exploiting the innovations in flexible PCBs. And we use the 3D printing materials like TPU to have comfortable textures. And also we tried in order to enable all the users or the researchers to use it. So we try to minimize the cost of the manufacturing. And also because of there's not large sets of the public training data for wearable device, so we try to use some self-supervised learning or some to harvest the training data from the videos to generate some simulated IMU data from the videos. And then we will discuss this, and we will discuss about the design principles of these OmniRings. So when we design these OmniRings, we especially consider about the social status senses to be able to like make the rings or bring the products or bring the technology into daily life. So regarding this, so we will consider to have the rings as clean as possible and as countable design for the users. And also we require that we want to have the longer battery and easy recharging for the users, because the ring doesn't have like some USB cable to be able to charge like our phone. So we have to consider some solution to be able to make a ring can be wireless charging. And also we will enable the rings to be able to like wireless communications using the Bluetooth. And also we want to like to enable the ring to cover the wide range of applications, because the wrist rings can apply to many different domains like sports or not just a finger motion, like sports or healthcare or any other domains. And also we consider that you can be water resistant, so we can do the further research using this range under the water. And lastly, also the range will be open source and then can be extendable to add more sensors, not just the IMU sensor or some health sensor like PPG sensors. And later I will discuss details about how what's the sensors inside this ring, and also what's the MCU we use in OmniRing. Okay, so this is the hardware overlook of the PCB overlook of our designs. So as you can see, is that we use the NRF 52832 as our main MCU. And the advantage of using this MCU is that we can enable to have a low power, and also we can enable to let MCU to communicate with a different sensor because we have a different communication protocol like SPI or I2C or UART. So we can use, so in this design, in our ring, we use the IMU. This is the initial measurement unit. So it can detect the 9 degree of freedom. It can have a 3 degree of the diameter and 3 degree of freedom of the compass and 3 degree of the meters. So with this 9 degree of freedoms, we can detect the finger motions, or we can detect the body motions of the users. And then we also have the PPG sensors. The reasons why we want to have the PPG sensor, because the PPG sensors can enable us to detect the blood vessels of the users. So we can detect some healthcare characteristics of the users. So we can detect the heart rate, blood pressure, or even glucose using the PPGs. And also this range will be embedded with the Bluetooth 5.2 wireless protocol. So it can be transit the data wireless. And this is also waterproof, as we discussed previously. And also this ring has a low power currently, so it can when you stream the data, it will take the 12 M8, but when it's in sleep mode, it will only have the 76 U8. And also for the weights, that we try to minimize the weight of the ring, so the users will not feel uncomfortable or difficulties when they wear the rings. So we minimize the rings as a 2.5 to 2.8, depends on the user's finger size. So regarding this, I think we have the compatible weights and size with the state-of-the-art product like OmniRing. And most importantly, this ring only costs $25. So the low cost can enable the users can enable the range to have a broader applications. And then we will discuss about the machine learning models of the OmniRing. So this is the overview workflows of our these papers. So at the beginning, we will extract the 3D rendering. We will extract the 3D IMU data from the public videos and to synthesize the data. And meanwhile, we will do some data augmentations so we have enough the training data. And meanwhile, we will collect the IMU data using IMU. And then we will have our own machine learning models to predict the 3D finger motions. And later I will discuss about how the accuracy of our papers. So this is the results of our OmniRing. So when OmniRing is stable to across the users and fingers when they checking the finger motions. So the checking errors is below to the 6.57 millimeters. And you can see is these two figures that the accuracy is stable and consistent across the users, 12 different users, and then 6 different positions. And then I will play the demo videos of how we use the 3 OmniRings to detect all 5 fingers. Okay, as you can see, is that even with the 3 rings, we can detect all 5 finger motions because we can, during the design, the machinery model, we find the correlations between the each fingers, and then using only 3 rings to get all 5 fingers. And also the finger can be, as you can see, the finger motion can be precisely detected when we compare our system with the ground truth. And regarding to able to enable more users or researchers to do this, to further develop the OmniRings, we also developed an app to do to enable to users to collect the raw data of this ring. So this on the left side is the app demo of the OmniRings, and the right side is the real play of the when we play the OmniRings. And also, we are welcome to everyone to download the apps on the Apple Store to access our raw data. So as you can see, is that when we collect the data using the app, we can get the high accuracy or 90 hertz, and also we can plug the raw data on the screen. So when the users or researchers using the OmniRing, they can visualize their data and then to extract the data from the mobile app. And then we want to discuss about the healthcare application, potential healthcare applications of this OmniRing. At this paper, we mainly just discuss about the heart rate detection of this OmniRing, because of the because we can based on this, we can see that the OmniRing can precisely to detect the heart rate using the PPG sensors. And also the heart rate is consistent, has a consistent arrow around the users. And then secondly, I will discuss about the EARFace. EARFace, this work is a joint work with my colleagues in Penn State, and we published this work in TIoT recently. So this system is to check the facial landmarks for the 3D facial reconstructions using in-ear acoustic sensors embedded within the smart earphones. And you can see we are using some TPU's materials, the 3D printing materials as our tip, and embed the MEMS ultrasonic microphone inside this tube, and then with the speaker. So when we use this, the purpose of this platform is to enable the users to enable the researchers to detect the facial expression, and meanwhile to minimize the discomfort for the users So when we develop this system, we also face some challenges, and because and also some concerns, because firstly, the traditional work is that we use some cameras to detect the facial expressions, but the cameras need to present in front of the users with a clear focus on the face at all times. And also we come up, and also is limited by the lighting conditions and image resolutions like we discussed previously. And so we come up with using the wearable smart earphones. So the smart earphones is robust to the ambient lighting, occlusions, and offers more portable check-ins. And secondly, currently most of the real world will use the outside air sensing with the sensors using electrodes like EMG, ECG. But its form factor can cause the discomfort because of the sensing. It happens outside the ears with the sensors. So they will protrude into the back of the head and slightly on the face. So they will make the users uncomfortable when they're using this device. So we come up with solutions to have design in-ear sensing using a sonic microphone to sense the shape of the air kernel in response to the facial expressions. And lastly, we will have the difficulty to how to map the air kernel change with the facial landmarks. So we will use, regarding this, we will use the ultrasonic reflections of the air kernel, and while the kernel frequency response to map the change of the air kernel with the facial expressions. To measure the change of the shape of the air kernel, the CRF is a compute. And also we apply the linear frequency central coefficient features to extract the features of the air kernel. And this is the overflow of the machine learning model of our EARFace systems. And this figure shows that as we detect the shape of the air kernels, we will detect especially detect the like facial expression of lips and eyes and nose. And EARFace can sense the change in the air kernel shape using ultrasonic reflections of the air kernel as captured by the ultrasonic captured by the acoustic sensors embedded inside of the earphones, as we discussed previously. And towards the measuring the change in the shape of the air kernel, the CRF of the air kernel is computed, and the LFCC is the feature is extract. And the machine learning model is based on the transformers and is designed to capture the rich spatial and temporal relationship in the air kernel CRF data. And finally, the model are trained to predict the facial landmarks, which are later will be converged into 3D facial expressions reconstructions by fitting the landmarks into parameters of the frame. The frame is a popular model for facial graphics and animations. And then we will discuss about how we bring up how we design our platforms. So in this platform, we use the dual MCU. We use the ESP32 as a communication MCU to transit the data from the platform to the mobile device like smartphone. And we use the Tensy 4.0 as data acquisitions MCU mainly to get the ultrasonic data from the microphone. And the microphone is its frequency is a range from the 18 hertz to the 80 hertz, 88 hertz, and also with the ESP32 it supports Wi-Fi, and it has a low, it's a very kind of high power consumption, around 245 mAh, and we use the LiPo battery around 500 mAh to power the data acquisition module, and so the earphone module can last for a long time. And so we discuss about the result of the EARFace. As you can see, we will measure the 8 different facial expressions like nature, happy, contempt, surprise, fear, anger, and sad, and disgust. So we can see at the beginning, we will have the ground truth to label our landmark. And then we are based on this figure, we can see is that our system can precisely to detect the facial expressions of the users. And later, this we will discuss about the result of this paper. And in this figure, we can see is that the CFR, our machine model is consistent across the multiple days for the same facial expressions of the users, and it varies with the change in the facial expressions. And although there are some similarities across the different users for the same facial expressions, but there are some difference due to this difference is due to individual difference in air kernel shape, which can be handled by the domain adaptations. And then lastly, I will discuss about the eyeball, which is a work by my advisor, Dr. Gaudat, with his colleagues and in his advisor in AYUC, as well as the collaborators from Intel. So this system is to check the crack case board 3D trajectories and the spins. When he designed this system, we still face some difficulties. For example, there's the orientation and rotation. So it's difficult to accurately measure the spin related metrics, such as revolutions per second and rotation axis. So this is a difficult characteristic for users to measure, but with this system, we can accurately measure it. And also we want to measure the initial orientation estimations. So while the geographical and symmetry provides the data before flight, so we can pinpoint exact initial orientation of the ball is with difficulties for us because of the noise and saturations. And also for the 3D trajectories, it's difficult to determine the 3D trajectory of the ball because of their speed and directions. And lastly, we will have some aerodynamic factors that will affect the ball's characteristics, so they will make the measurement difficult. So regarding this, we come up our platforms. So we embedded the IMU sensor data inside the crack kit. And then we use the UWB to sense the time of the flight of the ball. And with this, we can detect the motion and the 3D trajectory and spin of the ball. And then we can see that with this system, we can precisely to detect the spin of the ball with the rotation arrow under the 12th degree at the end of the flight. And as you can show in the figure, the red line represents the rotation axis arrow, and the green line represents the same planet arrow, and the blue line represents the orientations arrow. And then we can discuss about the location accuracy. So this figure quantifies the location arrows across the 50 different sources, and it shows that the median arrow is under 8 centimeters. And we can see the arrows in the different degrees, in S degree and Y degree and Z degree. So regarding these 3 words we have done, we consider that we can bring IoT into many different applications or domains like sports or facial expressions. And then with the IoT, we can empower us have doing more research related, help our research to further help people's daily life. And regarding this, we can add more sensors, such as temperature sensors, inside the wearables. And also we can embed we can empower like on-device computing. So we can compute the data, IMU data or PG data or any sensors data inside a chip. Because currently we are using some online algorithm. We train the data and then predict the results on mobile phones or online. So we can process or compute the data inside the chip. It can minimize the cost and minimize the power. And then we will further develop the healthcare monitoring, because of the we have the more sense like healthy sensor data sensor like PPG or ECG or EMG. And also recently we are doing some smart clothes work like as I show in the right figure. This new sensor can be embedded inside the smart clothes to detect the health data of the users and also detect the movement of the users. And when it detect the sensor detect the data from the users, we can stream the data to wireless to the mobile device. And lastly, we can consider about the authentication and some biometrics data to do some privacy related problems. And lastly, thank you for Professor Shari to invite us for this discussions. And yeah, if you are interested, welcome to scan this QR code to know we can have like further discussion or the collaborations. Thank you.
If you want to clap again, you can't hear you now.
Okay. Sorry. Thank you.
Okay. Any questions? Yeah.
Yeah, thanks. It's really good talk. So I don't have any background of the biology for the EARFace. How can you infer the facial expression from the ear canal chains? What's the basic knowledge?
Can you hear the question?
Yes.
Yeah.
Okay, let me share screen to explain it. Okay, can you see the screen?
Yes.
Okay, so regarding the EARFace projects, as you can see, is that we are using the idea is very simple. We are using or we are detecting the shape of the air kernel chains. So we are using some using the ultrasonic microphone to detect the reflection of the ultrasonic sound. So when we detect when the users is doing some phase, you have some motions on the air. So we can use some ultrasonics to sense the change of the motion due to the motions. And with this, we can use some CRF or LFCC to extract this change and map it to the facial expression landmarks. Does this answer your questions?
Yeah.
Yeah. So,
I have a suggestion for the OmniRing. Is that feasible to measure the heart rate or breathing rate by acting vibration? I noticed you integrate the IMU inside the OmniRing, right?
Yes. So your So your
so the
question
question
is
the question is, can you instead of PPG, can you use IMU itself to detect the heart rate? Is that what you're saying?
Yeah, can you just measure the heart rate or breath rate by detecting the vibration?
Without PPG?
Yeah.
so your question is asking whether we can use IMU to detect the heart rate without using the PPG.
Yes.
Okay, I think this is a very good question because the IMU is unable to detect the finger motions. So it may can detect the vibration inside the fingers or through the blood vessels. But I think this will be interesting topic or projects to using the IMU only to detect the blood pressure, to detect the heart rates.
Yeah. So I guess the frequency of motion has to be much lower than the heart rate. Then maybe you can decouple vibration from the motion. Is
Yes.
that right?
Yes.
Okay, the question about ear canal, maybe let me ask you. So people are surprised that with something you put in the ear, you can sense the facial expression. So maybe if I laugh, maybe it seems easy, but what is the what kind of expression is hard for you to detect with EARFace?
For the with EARFace, yes. So the difficulty for detecting the when we design the EARFace is that for the different users, you have a different share of the air kernel. And regarding this, we think it's the most difficulty because of it's difficult to do the user independent. So we come up with a solution like using the domain adaptations. So to kind of like to minimize the training data and also to able to make the EARFace is robust to the different users, the air kernel.
I see. So you have to train, you have a, you train across users and then you train per user.
Oh, no. We didn't train per users. We only train on one users, but we will as users to do a figure to do the pre-train then so we can apply some domain adaptations.
Right. So you do little bit of training per user.
Yes. Yes, using the image. Yes.
Yeah. Okay. And so go ahead. So, but the question was on which of those expressions you have happy, sad, disgust, and things like that. Which of those expressions is hard for you to detect?
The most difficult expression we think is about some slightly change of the facial expression, like anger of contempt, because this is a slightly change in the lips and the eyebrow. So we think this is the most difficult one to detect it.
Nice. Okay. Any other questions? Yeah.
I was wondering what do you best hope to achieve with the EARFace?
Did you hear the question?
No, sorry.
What's
your question?
With the technology EARFace?
What is the goal? What do you plan to achieve with EARFace? Where is the application scenario? Is that what you're saying? Yeah. What is the compelling, like a killer application for EARFace?
Oh, that's a good question. So, with the EARFace, we can detect the facial expression of the users. Regarding with this, then we can detect the emotions of the users, and also with the expressions, we can do some animation in the VR visual realities or MSR for the futures. So this is like some futures work we can do with the EARFace technology.
Also, yeah, you're thinking more like you can have an avatar and you put earphones and then in the avatar you show the expression.
Yes, and also with the expression, we can apply it to the sign language recognitions, because the sign language recognition not only related to the finger motions, but also related to the facial expressions. So with the facial expressions, we can predict or analyze the sign language more accurately, and then more understands that the language or the motions of expression of the deaf users.
I see. So EARFace plus OmniRing for sign language detection.
Yes.
Okay.
Yes.
Okay. Yeah. No, it's okay. Go ahead. There's time.
For EARFace, how much sensitive is the sensor for when the user is stationary or walking or they are in motion? Does it affect the sensing capabilities?
Do you follow? Like imagine the user is moving or shaking the head, things like that. Does it affect the expression detection?
Yes. So when we develop the EARFace, we also consider the motion effects on our system. So we are in this paper we slightly discuss about the head motions. So we found that the head motion didn't much affect our system is robust to the head motion, but regarding the like body motions or the this will be a very interesting topic to discuss, because we found that it's a difficulty to measure the facial expressions when users have is doing the exercise or have a big motion, body motion.
Right. Okay, any other questions? Yeah, go ahead.
Hi, Taiting.
Yes.
I saw his video showing that with the OmniRing, they use RS3 OmniRing there in that video.
Right.
So does that mean they need the micro range in order to detect the movement?
Yeah, so the question is you're showing 3 rings when you are doing the sign language thing. So do you need more than 1 ring for finger motion? Right.
What's the most, or is there a minimum requirement?
Yeah.
Okay. So this video is showing using 3 rings to detect all 5 fingers motions. But if you want to do some finger like the finger gesture recognitions, we can only have the 1 ring on the index fingers or the thumb fingers to detect the gesture recognitions. So the minimum, I would say, if it's just 1 ring or a simple gesture recognition, we can just have 1. But if you want to detect the 5 finger motions, what we find is that 3 rings of will be the minimal needs to detect it.
Okay. Can you go to the previous slide?
This one?
No, the previous.
This.
Yeah, so this is the yeah, actually no, I'm interested in looking at the heart rate, error in heart rate. Yeah, is that error good enough? Like you have 8 beats per minute, is that good? Or if you yeah, go ahead. Yeah. So it looks like the error is like 8 beats per minute, right? Yeah, average error in the heart rate. Yeah.
Yes.
So is that good enough? I mean, do you need to improve that to be more practical?
I think for sure because there's because of the because of this paper we just want to we just do a first step. We just want to show the proof this feasibility of this OmniRing. So we mainly just show that this as a BPM. So actually we can have a big improvement in the future. And this is also our current work that we try to solve. And also we consider about like some motion removal, because we have IMU data. We can use the IMU to solve or to minimize the motion artifacts on the PPG sensors, so we can detect the heart rate when user is shaking their fingers or doing any gestures or doing exercise. Yes.
How low can you go?
How long it can go?
Yeah. How low can you bring the error down?
I mean, where we will publish this work, or
yeah, no, I'm saying with the, is there any limitation on what is that error for the heart rate? Can you bring it down to pretty close to the accurate one?
Oh, what's the accuracy? What's the difficulties to bring the arrow down, right?
Yeah.
That's the question.
Yeah. So I'm saying, do you have any fundamental limitations, or you just have to improve it somehow and it'll work fine? I mean, you're still working on it, but I'm saying, how low can you make the heart rate? How the error in the heart rate? Is there any limitation on bringing the error in the heart rate down?
I think yes, there's some challenge because of the PPG sensor is sensitive to the user's skin tone and also sensitive to the motions. So I think there will be 2 main challenges to bring the arrow down.
I see. Okay, yeah, go ahead.
Going back to the EARFace, I was wondering what's the accuracy, and if you can collect enough data set what's the best accuracy that we can achieve?
Yeah, so for the ear face, do you have any expression detection accuracy? Graphs on
Yes, yes, we do. So as you can see, on this figure, we can, is it big enough to show this one? So we can see with the different expressions and with the frequency, we can see some, this is the amplitude is the, as the higher amplitude means that's higher accuracy. So with this, we can see that the error of the EARFace is consistent, and then below around the 12. Does answer your questions?
Could you elaborate more on these figures? I was wondering what was your input and what was your output? Was it a classification problem or a signal detection problem?
You can go to slide 17.
17. Okay.
Yeah. So did you do from the did you do the classification and look at the accuracy in the classification? That's the question, right? Yeah.
I was wondering if it's a classification problem here, or it was you got the signals in the sensor and you were training the model to predict the signal, if that makes sense.
Okay. So we are questioning about whether we are doing the classification problem, right?
Yeah, I mean, basically, I was hoping to see a confusion matrix, but since
yeah, do you have any confusion matrix you can show for this expression detection?
Yes, we do have the. Okay, firstly, we are not doing the classification problem. We are solving the lemma. So
I see.
Yes, so as you can see, the input data is ultrasonic data, and then we're using the techniques like CFR or LFCC to do the data pre-processing, and then we predict the result of the result of the predictions is the lemma of the users. So based on the
so you judge how good your scheme by looking at how close the ground truth landmarks and your landmarks are.
Yes.
Okay. Any other questions? Okay, any other questions online? Okay, then thank you. That's nice.